kidding. It's not on mechanical engineering. It's a self-balancing robot. So I am Ethan. That is.
My name's Yannick.
And basically, this is an inverted pendulum problem that is it's a naturally unstable system that we are attempting to stabilize. Its components are similar to a human body, where we are naturally unstable and will fall over just like a robot will. We have a brain, a measurement system, chassis, motors, and energy drink for power supply, obviously. And it sort of matches up to the human body. We have a brain to correct for when we fall, we can correct for it. Yeah, so naturally, we are unstable, just like the robot.
So, as you might have seen on the previous slide, the question was, is it hard to balance? So with human beings, balancing is pretty hard, as you could have seen from the baby's picture. But they can learn, but the robots can't learn. So we need to make sure that robots can imitate the human learning. And the way we, but first of all, we need to understand what the balancing is. First, how would the robot make itself balance? The way we do it is, once we've detected tilting, we should move in the opposite direction to counterbalance the tilt. And I guess picture describes it pretty well. To do that, we use the PID control, which would react as a system response, I guess. And it consists of proportional controller, integral controller, and derivative controller. On the next slide, you can see all that. But so, how does PID control works? Basically, P control allows you to reach the set point as fast as you can. But once you've reached that point, there might be steady state errors, which can all be eliminated basically just solely by proportional control. That's when the integral control comes in, and it allows you to reduce steady state errors. But only solely using P and I controls, you still might have oscillations. And in order to reduce those oscillations, you need to dampen them. And the derivative control should allow you to do that. So basically, working all together, PID control should finely tuned PID control allows you to reach the set point as fast as you can, and effectively you can work. This is the example of the code that we use. As you can see above, there are P, I, and D gains. Every time when our microcontroller goes into the PID function, it does it every 10 milliseconds. Why does it do it every 10 milliseconds? Because the accelerometer data generates at a frequency of 1 kilohertz, so pretty much over about 1 millisecond. But we did some testing yesterday, and we found out that the overall time that it takes for the controller, for the accelerometer and microprocessor to gather the data is 3.3 milliseconds. So we use 10 milliseconds to make sure that all the data is gathered and it is correct. And this is just a representation of what I was talking about, how PID control works. So increasing the gain, the P gain, allows us to reach the set point that there might still be a steady state error. Once you've eliminated steady state error by increasing the integral gain, you might still have some oscillations. And then the derivative control comes in and suppresses any gains or overshoots. And voila, it's balanced. Isn't that good? And even picks up from here, let's talk more about advanced layer implementation.
So, as of now, the system just uses MSP430 as we've been using in class, mostly because we were already familiar with it, and it was helpful for starting off with existing code, so we had a good baseline. Because this is a low-power device, it's specifically kind of opposite of what's required for a balancing system, and that has caused issues because we can't. It makes it hard to implement like powerful balancing algorithms because we have very limited instructions. As he said, it takes 3.3 milliseconds for us to grab the data and process it, which is severely limiting the control speed. And that for just a basic response system is taking 3.3 milliseconds without a complicated filter that would be desired for a better response. Also, it's small, so it fit on our small robot chassis. For the IMU, for reading what the angle is, because the MSP can't do it itself, we have an MPU 6050. It's just a cheap, easy-to-find accelerometer and a gyroscope, and it's very powerful and has a lot of things it can do. So it has an accelerometer and a gyroscope, and combining those two, first the accelerometer can read the values of G reference to the ground really fast, which is good, but it's very sensitive and produces a lot of noise, which is bad. So then we introduce the gyroscope, which is a slower response, but quite a bit more stable. And when you combine the two with something like a common filter or a complementary filter, which we're using, you can get an average reading of the both to get the good characteristics of both in order to have a good reference angle. It's just like if you're falling over, but you don't know that you're falling over, you can't correct for it. But if you can see that you're about to hit the ground, you can put your hands out or start walking forward so you don't fall. It's kind of helpful. So I've been implementing this. The issue is it's really hard to tune the system and build the code every time. So I basically have this, it's called a macro pad, and it can automatically send command strings to UART to adjust the gains. And that way we can work with the system to balance it, and hopefully as a demo for the expo we can live, you can see, hey, you can change the gains, see how the system responds. And then I also have set point offset, so if the robot, basically if your center of gravity is different than your set point angle of the whole robot, it wants to drift, because let's say it wants to be at 5 degrees, so you're leaning forward, the only way to not fall is to move forward. So we can change that reference angle to keep us from drifting. PCB design. To keep the system super simple and the wiring simple, I designed the PCB for everything to be mounted on so that the system is super rigid. It also reduces the errors in the readings from the IMU. And yeah, it just makes the whole system look much cleaner. It has multiple components on it. We have a voltage regulator to power everything from the battery. There's an H-bridge motor driver to take the battery power and drive the motors. Optical encoders we're not using yet, but we plan to implement some sort of velocity readout and position averaging. It has the IMU on board so that we can read what angle we are. And it supports distance sensing, which we haven't implemented, as well as a basic voltage readout from the battery so we know if the battery is dead or not. We have not implemented that yet. This is the motor driver and the magnetic rotary encoders. So basically we can drive the motors and read the position of them we haven't read the position yet, but we can for the velocity. This is the simple chassis with the PCB and everything mounted to it. I was using Lego tears in this picture to see if we could improve the motor response, and it definitely affected it. And the PCB makes the system super rigid and easy to work with, and if it hits the ground, it doesn't fall apart from all the breadboard wires. Back to Yesha.
And as Ethan was saying, we have noise in the system from the accelerometer and from the gyro. Gyro is not really noisy, but it drifts when it reaches high values. But the accelerometer is sensitive, but it doesn't drift. So in order to eliminate any kind of noise, we used complementary filter, which was easier to implement through the software. This is the basic diagram of how it works. And as I was saying, accelerometer needs a low pass filter, but the gyro needs the high pass filter. So together, combining them, they can give us good values. And this is the implementation in our software. The way it works is it combines the result from the gyro angle, which is calculated through the integration. It uses the previous angle, which was stored on the next step, and uses the actual angle, which is passed through the variable angular angle, and it's basically computed angle for the accelerometer. And every time whenever accelerometer reads an angle, the filtered angle accumulates, so basically like a sum. And since the processor works at 25 megahertz, it is able to show you the final angle pretty fast, so the accumulation happens really fast, which is great. And on the next slide I have the example of how it works. So the blue line is the actual angle from the accelerometer is drawn. The green line is the gyroscope angle in degrees, which was converted from degrees per second. And the red line is the filtered angle. On this picture, the weight or the filtering constant is 0.7. And you can see that it filters actually quite well. But on the next slide, we have filtering constant of 0.9. So it filters harder, which requires more time for the system to process it. And as you can see, when the accelerometer changes from negative 100 to plus 100 almost degrees, then the filtered angle doesn't change much. So it suppresses any change harder, but it also, if the angle will be at 100 degrees, it will take much more time to read this 100 degrees because it's accumulating more data. And the current issues that we have now is that the system doesn't balance, unfortunately, and we are working on implementing some ideas of how to balance it. One of the ideas is to put the IMU sensor higher so that the microprocessor can detect any inclinations, any angle inclination earlier to eliminate instability, because currently its position is quite low, close to the axis of rotation that might be an issue.
Also, to add to that, the error is from the pivoting point. The less linear motion error it gets, because so the acceleration will detect a linear motion, which throws off the angle calculation, which is obviously bad if you're reading the wrong angle from the actual. And as for the PID tuning in the code, that's a long, slow process, so implementing it over UART, which we are working on developing fully, should improve that greatly. So thank you for listening. Any questions?